Okay, in this video, we're just going to present formulas for calculating residues. Then in the next video, we are going to show how to use those formulas to actually work through some examples of how to calculate residues. So in the previous video, we defined a residue of a function f at a singularity, isolated singularity z0, to be given by this formula here. So as you can see, this is an integral formula where this is a closed contour integral around the point z0. So this would be your closed contour. This is z0 c. Okay, however, this formula number one we rarely use to evaluate residues. The formulas that we use mostly are the differential formulas, and here is the first one. If z0 is a pole of order m, then the residue of f of z at z0 is given by this formula here, which is just the limit as z goes to z0 of the m minus first order derivative of z minus z0 to the power m times f of z, and then divided by m minus 1 factorial. If m equals to 1, so for simple pole, this we're just going to replace every m by 1. Okay, so it's going to be 1, and that's going to be 1. So it just works out to the limit of z minus z0 times f of z as z goes to z0. Now, if z0 is a simple pole and f happens to be a rational function, so like p of z divided by q of z, then 3 actually works out to this much simpler formula. So the residue is just going to be p at z0 divided by the derivative of q at z0. So now we need to motivate this, so we're going to show you how this works out. Now, if z0 is a simple pole, then what it does mean is that z0 is a simple root of q of z. What does that mean? Of q of z. That means that q of z0 is equal to 0. Okay, so what we can do is we can expand q of z in powers of z minus z0 centered at z0. So this is going to be a Taylor series. So this is going to be q of z0 plus z minus z0 times q prime of z0 plus 1/2 z minus z0 squared, the second order derivative now, and then we can go on and on. However, since z0 is a simple root of q, what's going to happen is that this term here is going to be equal to 0, as we've already mentioned there. So that means if you expand this in a Taylor series, the first term is just going to be z minus z0 q prime at z0, and then the second term is going to be this one, and then the other terms are going to follow. So if we plug this into formula number 3, So remember, formula number 3 says the residue is the limit as z goes to z naught of z minus z naught times f of z. Now, so remember, we've said in this case f can be written as p over q. So this we can write as the limit as z goes to z naught then this is z minus z naught times p of z over q of z. And then what we're going to do in the denominator, we are going to express q of z using that Taylor series that we just derived. So this is going to be z minus z naught p of z divided by, now we said the first term is going to be z minus z naught q prime at z naught, and then the second term, okay, maybe let me just rewrite this so that we have got more space. So this is going to be limit as z goes to z naught, z minus z naught. Then we have got p of z here, z minus z naught q prime at z naught, 1/2 z minus z naught squared q double prime at z naught, etc. Now what you're going to notice is that we have got this common factor of z minus z naught in the denominator. So what we can do is we can cancel out here. So this cancels out with that, and that is going to be power 1. So if we do that now, we're going to have limit as z goes to z naught of p of z divided by q prime, this is prime, at z naught plus 1/2 z minus z naught q double prime, etc. At this point, we can plug in z naught because well, at this here at this step, if you plug in z naught, the numerator will be 0 and the denominator is going to be 0. So so we're going to do it now, because this one is now not 0. So if you plug in z naught, the numerator is going to be p of z naught. The denominator, only this term is going to survive, q prime at z naught, because if you plug in z naught here, this vanishes and all the other terms have got the factor of z minus z naught. And so that is going to be our final expression, which proves this formula, which let's call number 4. And so the last thing we're going to mention here before we do examples in the next video is what happens if z naught is a pole of order infinity. If z naught is a pole of order infinity, which is called an essential singularity, if z naught is a pole of order infinity, that is an essential singularity. Okay, what we do to find the residue, we find the residue by, because as you might imagine, So this was the formula for pole of order m. So pole of order infinity will suggest that this has got to be plug-in infinity here, here, and there, and that is going to be a bit of a problem. So what we do here is we find the residue by expanding in a Lorentz series and then looking for the coefficient of the term to the power -1. So we find the residue by expanding in a Lorentz series centered at Z0, and then examining the term involving z minus z0 to the power -1, because then the coefficient of that is going to be our singularity. All right, so that's that in terms of the formulas. So in the next video, we're going to look at a few examples and see how these formulas come to play. All right, ciao.